Hi everyone, in this video we're going to look at OR probabilities, which are calculated using what's called the addition rule. So here's an example that you'll recognize if you watched the mutually exclusive events video. We're doing an experiment where we randomly select a US senator, and we have two possible events that we're interested in. Event A is that the senator we select represents California. Event B is that the senator represents Texas. In the mutually exclusive events video, we talked about how these are mutually exclusive. We cannot have event A and event B happen at the same time. So the probability that we'd be looking at here is, what is the probability that a randomly selected senator was from California or from Texas? So this key word here is or. This or is telling me that I need to be using the addition rule. The formal statement of the addition rule looks something like this, and I have this stated in two ways. The probability of A or B, so the probability of one event or another event, is the probability of A plus the probability of B minus the probability of A and B. In this scenario, if A is the senator being from California, and B is the senator being from Texas, the probability of A would be, well, how many senators are there from California? That would be 2. Out of how many total? That is 100. And then probability of B, how many senators are from Texas? That is also 2. And then out of how many total? That's also 100. And then in this case, the probability that a senator is from California and Texas in terms of representation is 0. This is not possible. Because these are mutually exclusive events, that overlap, or the and portion, is always going to be 0. You'll see alternate notation for this. Instead of A or B, we might see a union B using the union symbol here. And then instead of A and B, you would see the intersection symbol. They really mean the same thing. The intersection is the overlap between the two, and the union is sort of everything in A together with everything in B. Another example, again, I use this in the mutually exclusive events section. So we're looking at event A is that we randomly select a senator from the Finance Committee. Event B, that we randomly select a senator from the Judiciary Committee. This is an example of two events that are not mutually exclusive because there are senators that fall on both committees. So in this scenario, if we want to find the probability that a randomly selected senator was on the Judiciary Committee, I'm going to call this event A, or on the Finance Committee, I'll think of that as event B, then I'm going to use this addition rule. And again, this is just two different statements of the same rule. I'm going to use this one below here. So the probability of A or B is the probability of A. Well, the probability that our randomly selected senator is on the Judiciary Committee is how many senators are on the Judiciary Committee out of the total. I know that the total is 100. There are 100 senators in the US Senate. And then I'd look at the list of the senators in the Judiciary Committee. Again, I just compiled one of these lists and put it into Excel. There are, I believe, 27. Yes, I see a count of 27 down here. There's 27 members on the Finance Committee. Oh, sorry, I got that one backwards. So that one was for B. So the Finance Committee has 27 members. The probability of getting someone on the Finance Committee would be 27 out of 100. And then for the Judiciary Committee, I'll look at how many were on the Judiciary. Again, just looking at the list, counting up how many there were. Looks like that is 22. So I have 22 out of 100 plus 27 out of 100 minus, and then I need to know how many, in this case, how many senators are on both committees. This represents the overlap. In this case, when I counted up the 27 and the 22, there were people who were in both lists. So I don't actually want to count, for example, John Cornyn from Texas. I don't want to count him twice because he doesn't represent two different senators. And that's why we do this subtraction at the end to take out kind of the double counting. So within this 22 and this 27, there were 5 different senators who got counted twice. So we take out that overlap, and that gives me 22 out of 100 plus 27 out of 100 minus 5 out of 100. In this case, you could just do this by adding up the number on this committee, the number on this committee, minus the number on both, and then taking it out of 100. You'd get exactly the same thing. But sometimes these probabilities are not all out of the same amount, right? You might have just percentages or decimals. These probabilities can come from any type of computation. This calculation would still be true. In this case, the total probability ends up being 44 out of 100. I could leave that as is. I could reduce the fraction and get 11 out of 25. I could also write this as a decimal, 0.44, or as a percentage, 44%. You'll see answers like all of these possibilities as possible values for probabilities. All right, here's another example. Suppose that there's a test for a fictional disease called testovaria, and we have some data collected on this test in the table below. So this table has some rows and columns. So each row we have positive tests, so the people who tested positive for this disease, and then we have negative tests, and then we have the total. And then in the columns we have has the disease, the next column is no disease, and the total. So in the first box, this would be under test positive and has the disease. That's 90 people tested positive for the disease and they really had the disease. In the next box, we have, this is the test positive row, but the no disease column. So this is people who tested positive for the disease but didn't really have it. We often will call these false positive results. In contrast, the number 90 was the true positive results. And then the total, that would be the total of this row. That's all of the people who tested positive, whether they had the disease or not. So 150 people tested positive. Similarly, in the test negative row, we have 90 people who tested negative but have the disease. They should have tested positive but tested negative, so these are false negatives. And then 840 people tested negative and did not have the disease. These are correct results. These are true negative results. And then again, we have the total of all the test negatives. That's just the 10 plus 840, and we have the total here as 850. The total row at the bottom has the total of everyone who has the disease, so 90 plus 10 is 100. The total of everyone who did not have the disease, 60 plus 840 is 900. And then the total of the totals, which is 1,000. So this 1,000 represents everyone within the data set. So here's a probability question we might ask based on this data. What is the probability that a person has the disease or gets a false positive? So first of all, I'm looking at this key word here, or. This is my indication that I need to be doing an addition rule calculation. So I'm going to look at the people who have the disease, so that's everyone in the has disease column, as well as people who get false positives. The false positives were the positive tests where the person actually didn't have the disease. In this case, that's just the 60 people who tested positive with no disease. So these two groups, a person who has the disease or two events, or a person who gets a false positive, these are mutually exclusive. So when I do my calculation, there's not actually going to be an overlap between the two events. So I can still use my addition rule, but I'm going to see the probability of A and the probability of B, and then the probability of A or B, this is just 0. You cannot have the disease and get a false positive. Those are contradictions, because if you have the disease and test positive, that would be a true positive. So I'm going to look at what's the probability that someone has the disease. There were 100 people who had the disease out of a total of 1,000. Plus, what's the probability that someone gets a false positive? That was 60 people out of 1,000. And then I could say minus 0 here, but I don't really need that overlap because these are mutually exclusive events. This would give me 160 out of 1,000, or again, I could do the reduced fraction or a decimal or however you want to represent the probability. Here's another example. What is the probability that a person has the disease or tests positive? This is a similar setup. This is an or probability. We're looking at event A or event B. In this case, the event that a person has the disease, that's the same one we were looking at before, that's these 100 people who have the disease. And then the event that someone tests positive, that would be any of these people in the test positive category. There were a total of 150 of those, but there is an overlap between these two groups. These are not mutually exclusive events. So when I calculate the probability, I'm going to find the probability that a person has the disease, that's 100 out of 1,000, plus the probability that a person tests positive, that's 150 out of 1,000. But when I add those 100 and 150 people, I am double counting these 90 people who both have the disease and tested positive. So with the addition rule, I would then have minus 90 out of 1,000, which takes out that extra probability that was really double counted. Alternatively, when you have these table problems, rather than doing specifically the addition rule like this, you could just take all of the different groups that would apply here. In this case, that would be the 90 people who have the disease and tested positive, the 10 people who tested negative and have the disease, and then the 60 people who did not have the disease but did test positive. You could just add all those together and take that out of 1,000. You get the same answer. They're really doing the same thing, just a different approach. What's important here is that when you have overlaps like this the 90 people here, that you're not double counting those possibilities. That's it for this video. Thanks for watching.